Good morning, everyone. My name is Kang from Northwestern Polytechnical University, China. As the first author, do not come here due to the problem of visa. So today I will present this work, Summation of Eigenstates as a novel output metric to extend the linear sensing range of mode-localized sensor. I will introduce this work from 4 sections. As we know, MEMS resonators are the key mechanical sensing elements for measurements of physical parameters. The traditional resonant sensors are based on frequency shift, which limits the sensitivity and robustness. In 2006, a new kind of resonant sensor based on mode localization was proposed for the first time and applied to the mesh sensing. The sensitivity was enhanced by 2 orders of magnitude compared with traditional frequency shift-based sensor. After that, the resonant sensor based on mode localization was applied to various physical parameter sensing, such as displacement sensing, stiffness sensing, and acceleration sensing. The new transduction scheme based on mode localization is promising to improve the performance of resonant sensor. What is mode localization? Here I want to use a 2-degree of freedom resonator to explain the mode localization. The traditional resonant sensors are constructed using one resonator. Then we weakly couple the 2 identical resonators together. The weakly means the coupling stiffness is much smaller than the stiffness of the resonator. When perturbation caused by the change of stiffness or the mass introduced to the system, even the perturbation is very small, the vibration mode shape will be drastically changed. From the magnitude and frequency responses of the 2 degree of freedom weakly coupled resonator, we can clearly see that the amplitude of the 2 resonators changes very obviously after the perturbation is introduced to the system. As we know, most of the resonators are based on single degree of freedom in the market. For the single degree resonator, only the frequency and the amplitude can be used as output metric, where for the multiple degree of freedom resonator, except the frequency and the amplitude, more amplitude-related output metric such as amplitude ratio, amplitude difference can be used as output metric. If the amplitude ratio is used as output metric, the sensitivity can be enhanced by orders of magnitude compared with that based on the traditional resonance frequency readout, because the coupling stiffness is much smaller than the stiffness of the resonator. Then the resolution will be improved. Furthermore, the output metric of amplitude ratio can reject common mode noises such as temperature, humidity, and pressure. However, the improvement of the sensitivity is accompanied by the loss of linearity and the linear sensing range. The problem of nonlinear sensing is due to an inherent characteristic of a mode-localized sensor. For mode-localized sensor, the amplitude ratio of the 2 modes firstly approach and report each other quickly after approaching the varying point. The varying point is defined as a point where there is no stiffness perturbation and the amplitude ratio is 1. Due to the loci veering, the linear sensing of the amplitude ratio is limited to either the left range or the right range of the varying point, depending on which mode is selected as the working mode. If the amplitude is used as output metric, the linear sensing is only near the varying point, and the sensitivity based on amplitude is much lower. Although the sensitivity based on amplitude difference is much higher, the linear sensing is also only near the varying point. It can be seen that all the amplitude output metric are not linear function of stiffness perturbation in the first skew range. The first skew means the range of stiffness perturbation continually varies from the negative to positive region across the varying point. How to improve the linear sensing range of the mode-localized sensor? Some researchers have to manually adjust the initial working point to improve the linear sensing range. It can be seen that the for first-degree linear sensing are not still realized, and it introduced complexity to the sensor design. Until now, there isn't any method to realize the first-degree linear sensing for mode-localized sensor. In this work, we propose a new method to realize the linear sensing in the first-degree range. The output metric of amplitude ratio is the most popular one for the mode-localized sensor. When we add the amplitude ratio of the two modes, it is obvious that the summation of amplitude ratio of the two modes is a linear function of the steadiness perturbation in the first-degree range. Therefore, the first-degree linear sensing can be realized by selecting the summation of amplitude ratio as new output metric. Furthermore, the sensitivity based on the summation of amplitude ratio is higher than that based on the amplitude ratio. In this work, a stiffness sensor implemented using a 2-degree of freedom weakly coupled resonator is used to verify the proposed first-degree linear sensing method. The weakly coupled resonator was constructed using two double-ended tuning fork resonators weakly coupled by the mechanical beam, and the 4 tuning electrodes around the two resonators were used to generate the electrostatic negative stability perturbation. The device is electrostatically driven and capacitively sensed. The frequency responses of the two resonators are observed and recorded on the dynamic signal analyzer. The device was tested using in a vacuum chamber with a pressure of 20 millitorr at room temperature. A 25-volt DC voltage was applied to the two resonators, and the 20 milli AC sweep signal from the dynamic signal analyzer was applied to the drive port of the resonator 1. Then the output signal were amplified by the transimpedance amplifier and observed on the dynamic signal analyzer finally. By adjusting the voltage applied to the tuning electrode, the effective stiffness of the two resonators can manually controlled. Thus, the device can be regarded as a mode-localized stiffness sensor. To verify the proposed first-degree linear sensing method, we extracted the amplitudes of the two resonators at the two modes and drew the variations of the amplitude ratio of the two modes. It can be seen that an obvious loci variation emerges when the stiffness perturbation goes through the point of minus 6.95 Newton per meter, which separates the amplitude ratio of the first mode into two parts: the left region with the better linearity and sensitivity, and the right region with the awful linearity and sensitivity. The bearing point is not localized point with no stiffness perturbation, because the two resonators are not perfectly symmetric due to the fabrication tolerance, causing the mismatch of mass and the stiffness between the two resonators. Therefore, the linear sensing is limited to minus 12 to minus 8 Newton per meter when selecting the amplitude ratio of the first mode as automatic. The largest nonlinearity error is about 45% in the first-degree range, and the sensitivity is about 0.85 per Newton per meter in the linear range of the first mode. Similarly, the linear sensing of the second mode is limited to minus 6.5 to minus 2 Newton per meter, and the sensitivity is about 0.87 per Newton per meter in the linear range of the second mode. It can be seen that neither the amplitude ratio in the first mode nor the second mode is linear changing around the varying point. Thus, the first-degree linear sensing cannot be realized. In the contrast, the summation of the amplitude ratio of the two modes is a linear function of a stiffness perturbation in the first-degree range of minus 12 to minus 2 Newton per meter, which is more than 2 times larger than that when selecting the amplitude ratio as output metric. The linear fitting function between the summation of amplitude ratio and the stiffness perturbation was obtained. The nonlinearity error is about 1.36% in the first-degree range, which is improved significantly compared with that of amplitude ratio. And the sensitivity is about 0.9 per Newton per meter in the first-degree linear range. which is a little higher than that of amplitude ratio. In summary, the purpose of the new output metric of summation of amplitude ratio do not realize the linear sensing in the physical range, but also improve the sensitivity and nonlinearity error. In this work, we for the first time proposed a method to realize linear sensing in the physical range. The experimental results clearly demonstrate that the physical linear sensing can be realized using the summation of amplitude ratio of the two modes. The purpose of the physical linear sensing method has greatly helped to extend the linear sensing practical application of the mode-localized sensor. At last, I want to thank the support of the National Natural Science Foundation of China. Thank you very much.